Thank you. Please. Okay, so yeah, let me start by thanking the organizer for giving me the opportunity to speak here. So yeah, so the thing that I'm going to talk about, yeah, again, not much related to MBL, but of course there is thermalization here. So before starting, so just acknowledge my collaborators. So all this work that I'm going to describe have been done by these three people. Orijit, who was at the institute, I'm there, I mean, where I am, the Indian Institute of Science. So he was a student there, now moved to UToronto. And graduate student Surojit and Prosenjit, who was also a postdoc now. Okay, and this work started with some earlier work with Ehud Altman. So what I'm going to discuss is some overview of that and mostly some more recent works. Okay, so this work, so what I'm going to discuss is actually very simple thing that on what we are hearing today. I'm essentially a toy problem that I'm going to discuss. So I'll be talking about actually a low temperature, temperature asymptotically approaching zero temperature basically, and there we'll be talking about some quantum phase transition, but I'll show that the transition that I'm going to talk about is really not a ground state phase transition in the usual sense. But anyway, in the usual quantum phase transition, typically if you have a finite system, then depending, so you have some parameter, two parts of Hamiltonian, and you tune one part of the Hamiltonian with respect to the other, and depending on what kind of terms these are, you can have either some actual level crossing or some avoided level crossing. And when you go, of course, to infinite system, then this avoided level crossing could be very sharp, and essentially you can have a transition. Now, so what I'm going to discuss in this kind of toy example that I'm going to take is kind of an unusual quantum phase transition where, so there is something G here which is cut, but essentially similar setup that you tune some parameter and there will be some quantum critical point of certain nature. However, this transition is kind of an unusual type. So this transition, as I'll try to argue, that there is nothing much that is going to happening in the ground state in this case. However, what is changing here is near the ground state in one of the phase, let's say where G is less than Gc, you have exponentially small level spacing of the spectra near the ground state. So let's say there is some ground state and there is very small level spacing. And the transition is unusual nature because when the transition happens, this basically becomes some polynomial, the level spacing becomes some polynomial. So the reason if you, since there is a exponentially small level spacing near the ground state, actually some of the physics that we are hearing about thermalization and all, in some sense also appear here because of this very large level spacing, even near the ground state, this become very effective thermalizer. Okay, so it thermalizes very fast, and in fact, in this kind of model, it is the fastest thermalizer known in nature. I mean, of course, it probably doesn't exist in nature, but I mean, if in a model sense. And so this is the kind of particular non-Fermi liquid state that I'm going to discuss, and then the transition would be something I'll call a Fermi liquid, where interaction effect is essentially perturbative. And I'll try to argue that these are two type of different thermalizing fixed points, so which will also be basically quantified by chaos. Okay, so I'll try to discuss this. Okay, so the toy model that I'm going to take is this model Sachdev-Kitaev model, which have now become quite famous. So many of you probably know about this model and heard talks about this, but let me just, sake of completeness, let me just introduce this model. So this is a zero-dimensional model in sense that it's basically infinite range. There is no sense of space here. So you have n sides and you have fermions which are interacting with this 4 fermions term, and they are interacting with some random coupling which is taken from some random Gaussian distributions, and all fermions are interacting with all other fermions in this kind of pair hopping process. Okay, so the reason this model become kind of interesting, starting with the work by Sachdev and Ye, and then interpreted in a nice way by Kitaev in more recent times. The reason is that this model in the thermodynamic limit, meaning the large n limit, become exactly solvable and is strongly interacting, and it has a non-Fermi liquid ground state. And it has some interesting reparameterization symmetry at low energy, which emerges at low energies, not there at high energies. And moreover, in this model, there is kind of a thermalization rate that you can calculate exactly. So it's a strongly interacting model, but even then you can calculate some kind of thermalization rate, which is kind of rare in this type of model. And this thermalization rate is characterized by a Lyapunov exponent, which is written as lambda L, and this is in certain units, kb equal to 1, h bar equal to 1 is exactly 2 pi t. Okay. So it turns out that this limit, as you know, that is kind of special. This is something that any quantum system can have. The maximum that any quantum system can have in nature is called Maldacena-Shankar-Stanford bound. It is the upper bound of chaos. Okay, and this model actually saturates that bound. So it's extremely chaotic, maximally chaotic model. Okay, so now what I'm going to talk about in this, it is inverse of time scale. So T is temperature, sorry. Okay, so now the outline of my talk is like this. So what I'm going to discuss, as I said, that there will be a quantum phase transition that I'll be discussing, where what happens is the many body spectrum near the ground state radically changes across some transition as a function of this tuning. And so what I'll do is I'll try to introduce a little bit more about this SYK model, just what we need to discuss the consequent things. And then I'll try to show that there is this model which can describe a transition where this level spacing actually captured by some zero temperature residual entropy, which actually continuously vanishes at this transition. Okay, and then I'll discuss some dynamical phase diagram, some large N and exact diagonalization calculation, and probably I'll not get time to discuss quantum coins, but maybe I'll mention at the end if I have some time. Okay, so just to discuss SYK model, so it's actually very simple to do this. I mean, if a very simple type of Green's function method that you use. So this model, so what you look into is this kind of disorder average Green's function, and typically, of course, always you can write a Dyson equation with the self energy. Now, what is special about this model is this solvable, meaning that in this limit, large N limit and disorder averaging. So only self energy diagram that contributes is this very simple diagram, where this thing that appears here is the imaginary time Green's function, but the exact Green's function. It's a self consistency equation that you have to solve, and this is pretty easy to solve in a computer, okay, and you can sort of calculate all the properties of the model. But what you can understand without doing this solution is a very nice thing, which why the model become kind of interesting. So if you look into this Dyson equation, and let's say for you neglect this term omega to start with, and we are working with half filling where mu is actually 0. So if you neglect this term omega, so then actually you can rewrite this Dyson equation in this form, and then you can show that so basically this happens when you are at low energy, that this omega or temperature is much smaller than this J. Then you can do this process, and then you can find that this Dyson equation along with this self energy expression has this very large symmetry that emerges. That is that if you scale the time, so basically reparameterize the time with some arbitrary monotonic function, then you will find that this equation is actually invariant. Okay, so if you change the time, reparameterize time like that, and also change the Green's function with certain fermion scaling dimension, then this equation will remain invariant. Okay, so this is the low energy thing that appears, and since there is this large invariance, you expect a power law solution, and indeed you can show that there is a self-consistent solution of this equation at low energies, which is basically, if you look at g of tau, is going like 1 over square root of j tau. And if you look at frequencies, it goes like 1 over square root of omega, which is shown here. If you look at the spectral function, it basically diverges at omega equal to 0. So these are the spectral feature of this model, and you can indeed see that this is a non-Fermi liquid, because if you look at the self energy is all what matters at low energy. So the self energy is much larger than omega, as omega tending to 0. So everything essentially controlled by this interaction, okay, at this low energy limit. So you can also, which I will not be talking about, you can also calculate this chaos here, which was done by Kitaev. So you can calculate this out of time order correlator, the particular one shown here, but you can calculate many others, it will give the same result. And what happens in the leading order in 1 over n, you get this exponential, so in this case exponential decay of, not really exponential, 1 minus this exponential type of behavior, and this lambda L you can calculate exactly, which is 2 pi t. Okay, and that, as I showed, this is the maximal value. Now the thing that I am going to mostly focus on in my talk is, as I said, about this level spacing near the ground state or the residual entropy. So if you do this large N calculation on a computer, and let's say you calculate this saddle point entropy, then what you will find, what is shown here from this paper, and you can do this calculation quite easily. So if you look at entropy per site, then you will find that as you go to lower and lower temperature, this goes to a finite value. If you take the limit in this way, meaning in this calculation you have first taken n tending to infinity limit, and then you are going towards t equal to 0. In that limit you will find that there is a finite entropy. Okay, so you might think that this comes from some degeneracy of the ground state, but it is not actually true. So there is no ground state degeneracy here, not extensive ground state degeneracy. What is happening here, essentially what I started with, is basically if you look into this kind of SYK model, near the ground state the level spacing is exponentially small, or energy level is actually exponentially dense. So if you look at any temperature window, finite temperature window T, there will be exponentially large number of levels, and if you just count that, it will give an entropy which is finite, extensive entropy density. Okay, so that's the physics of this model, and somehow large N calculation is able to capture this effect, which is kind of quite weird, but it is able to do that, and so that's why this entropy comes. Okay, and this is very unlike a conventional many body system where this kind of exponential level spacing only appears at very high energy, but not near the ground state. So in this sense, some of the physics at very high energies you can mimic in the SYK model, even near ground state, where you can do this kind of calculations, okay, with some control. So that's one of the interest, I think, in condensed matter with this kind of model and its variance and variants. Okay, so this also has some interest that people would like to think about this entropy as some entropy of Hawking entropy of some extremal black hole and all, but anyway, I'm not going to go into that. So this is the thing that this is the interesting part, that you have this exponentially small level spacing. So as a result, we would expect that the thermalization and everything become very efficient in this model, and that's what we are going to discuss. Okay, so now one of the questions, so this of course was understood in 2015 or 16, right after Kitaev work. So one of the things that people are thinking about in this field, I think recently, is what happens if you not try to take the limit the other way around. Okay, so if you try to do a calculation at finite n and then try to take t equal to 0 limit, and this problem is of course not solved, but people have made some progress along this line. So let me just summarize that. I mean, I'll discuss a little bit of this in our exact diaggramation study. So to understand what happens, what you have to do to approach this limit, this other way of taking the limit, you can go back to the saddle point equation. So what you find that in the saddle point equation you neglected in this Dyson equation, you neglected this term. Okay, and as a result you had this very large symmetry, this reparameterization symmetry under which this equation was invariant. Now, once you find the saddle point solutions, however, that saddle point solution do not obey this symmetry. It's like if you solve the mean field equation of Ising model, you will find a solution either plus or minus. So that saddle point solution will certainly break that symmetry. Okay, so it turns out that this saddle point solution that I wrote earlier, or this 1 over square root of tau, actually has a smaller symmetry, which is just SL2R. Okay, which is, if you now reparameterize with this thing, then this equation will be invariant, which you can show. And now as a result, what happens is that there is a Goldstone mode that appear in this system, which is basically this thing. So this some Goldstone mode that remains, and you can actually calculate the action for this Goldstone mode. Okay. Discard what? Okay, so that's a good point. So the thing is, right, so when you actually generate this Goldstone mode action, you have to bring this W or delta tau term back, and that actually generates this non-zero action. Okay, so that term is taken into account to generate this action now. Okay, so basically that's what you get. So now you can see that this thing has a prefactor which actually depends on n, and you can show that if you include this effect, that as was shown by these people, that actually this 1 over square root of omega divergence changes at low energy. In fact, if you go below the single particle level spacing, which is like 1 over n, so here there is some renormalization, whatever 1 over n log n. So if you go below that, what you will find that this now, rather than 1 over square root of omega divergence, you actually get a square root of omega term, with a prefactor which is very large, n log n. Okay, so this is what happens if you try to incorporate the finite in physics. But really, to answer this question, you actually have to resolve the many body level spacing, which have not been done yet. So people have only been able to sort of resolve this single particle level spacing. So there are some open questions you can ask, that if you try to incorporate this, then what happens to this level spacing, whether it changes, etc., etc. So that are not known. Yeah. Yeah, it's not complex here. So here it is real. Yeah. So that I showed, right? So if you neglect this term, you can show that you can reparameterize this time, and then equation remain invariant if you properly scale the G. So that's what I showed earlier. Yeah, so that's the point, right? So this is a 0 plus 1 dimensional system. So that's why actually what happens is that these saddle points will be actually destroyed because of this effect. So that's why this effect comes, that it becomes square root of omega, because this Goldstone mode ultimately destroys this order, okay, at an infinite temperature. Yeah. Okay, so now the question, let me come back to the question. So now what we are interested, so this is all good, and you have this nice this model where you can go from basically you can describe some kind of thermalization and this kind of level spacing. So now the question was that how can you basically get a non-Fermi liquid to Fermi liquid transition. So essentially try to change this thermalizing behavior. So one type of fixed point, which is this SYK fixed point, which has this maximal chaos and this very large number of levels near the ground state. So if you can try to change this, okay, at very low energies, because you want to use this effect. So now one thing you can try to do, of course, that you can try to add a term which is like a natural term, which is this quadratic term with some random term with certain scaling, so that you can solve it exactly. And what you will find, that if you add such a term, then this term is always relevant, and there will be always a Fermi liquid, there will be no transition. So that means any value of this parameter T, it will never have this SYK non-Fermi liquid, it will be immediately destroyed. So the question is that if you want to study this kind of transition over extended region, so there is a phase and then there is a transition, so you have to do something. So let me mention one thing, that there could be still a non-Fermi liquid state at finite n, but I will not go into that. Okay, so this is basically this earlier work that we did to try to show that how to actually get this kind of non-Fermi liquid to Fermi liquid transition. There are some other models after that people have proposed. So the idea is actually again very simple, and it turns out this is a kind of simple way to do it. There may be many other ways to do it. So what you do here is actually you introduce two sets of fermions. So these C fermions, which are these SYK fermions, and then these other fermions which are sort of non-interacting on their own. So they are living on M sites, and they basically are described by this kind of quadratic hopping terms. Okay, so now of course you have to couple them. So you couple again with the simplest possible term with this kind of, again all these couplings are completely random with some Gaussian distribution, and you scale this term such a way that you have this solvability in the large n, meaning that the large n limit that you seek here is this kind of limit. So you try to take the n and m, this number of sides of the SYK fermions and number of sides of the psi fermions, this non-interacting fermions going to infinity, but you keep this p, which is this parameter m by n fixed when you take this limit. Okay, so I will not go into the detailed calculation of this. This is something that we did some time ago. So let me just summarize. So if you do this, what you get? So you indeed what you find, that you get a transition as a function of this parameter p, which is basically this ratio of m by n. You indeed get a transition exactly at p equal to 1, and this p equal to 1 doesn't depend on other parameters of the model, meaning the strength of these terms, it doesn't depend. So it's always p equal to 1. And what you find, that below this p equal to 1, you have a non-Fermi liquid state which has exactly this 2 pi t. So the full phase has this maximal chaos that you can exactly show. And then you find that that you can actually calculate exactly the zero temperature entropy, meaning this level spacing, and you can show that this zero temperature entropy actually goes to 0 continuously, okay, at p equal to 1. And so the way to interpret that is basically you have this level spacing which is going like e to the power s0 n, and this s0 is a function of p which continuously goes to 0 at p equal to 1. And if you go beyond p equal to 1, you find that this become a Fermi liquid, meaning that your lambda L is basically going like T square, and you can show that this entropy is basically 0. Okay. And another thing what you find is that there is a transition also in the spectral function, meaning if you look into the non-Fermi liquid state, you always find this 1 over square root of omega divergence in this side, whereas if you look into the other fermions, so now you have two fermions, the C fermions and the psi fermions. So there are two spectral functions. So the other spectral function is square root of omega, and this one is 1 over square root of omega. And when you go to the Fermi liquid side, basically at low energies, both the spectral function effectively become constant. Okay, so this is the characteristic of transition. So you have a transition in the spectral function, you have a transition in the entropy, the residual entropy or the level spacing, which is changing like this, and you also have a transition in chaos. So you are basically going from one kind of thermalizing behavior to other kind of thermalizing behavior. Now actually it turns out that some of these things can be realized, at least there are some proposed realization of these models in some real physical systems. So let me very briefly go over that. So this is the so there are several proposal of realization of SOIK model in condensed matter system. So this is one of the proposal which is I think kind of very simple and may be realistic, although it's very hard. So what you have here is basically you can apparently realize this physics in this kind of graphene nanoflake. So what you need a graphene nanoflake which is kind of ordered in between, and there is some irregular boundary, and you need to apply some magnetic field. So it turns out that there is some theorem which is Aronoff-Kashar theorem. You can show that even if you have this kind of disorder, that is the boundary is irregular, so even then when you apply a magnetic field in a graphene flake, actually you still get a zero energy manifold which is n-fold degenerate, where n is the number of Landau levels that enter. So the degeneracy of the Landau levels, which is SB by phi 0. Okay. So it turns out due to this irregular boundary, when you now project into this zero energy manifold the interaction term, you can actually get basically you can get rid of this term because of the zero energy manifold, and if you project the Coulomb interaction, you can actually get like the SOIK term. Okay. So this is a proposal that is there, and you can actually realize the model that I mentioned. So these people actually showed that if you take this graphene flake and if you connect to M channels lead, then actually this M channel effectively act like this M sites that I was mentioning, this non-interacting fermions, and you can tune this M by N, which is this P, and what they showed that if you have such a device, if you look at the tunneling conductance, then you should see at universal jump exactly at this quantum critical point that I mentioned. Okay. So anyway, this is very hard to realize, but there are some proposal to realize this. But let me go into now basically focusing on this physics that I want to discuss in rest 15 minutes or 12 minutes or something. So one of the things that that I asked earlier, that basically if you try to take the limit other way around, that if you try to take the finite, you look at finite n and then try to take t tending to 0 limit, then what happens? So here is some work, some exact diagonalization study, which of course are limited to small system size. So here some exact diagonalization study that we did and calculated the spectral function. So these are some systems with total number of sites which is 12, but we have done till 18 or so, or 16 or 18. The basic feature remains same. So what you find that if you look into the spectral function, you see even with such small system, you see very similar feature, meaning if you are p less than equal to 1, p less than 1, like let's say p 0.33, you see that this diverging kind of spectral function, and as you increase the p, you can see that the spectral function eventually tends towards a constant. So this is for the C fermion, the SOIK fermions. Similarly, if you look into this kind of non-interacting fermions, you see very similar result that you expect from the large N. Okay, so even though system size is so small, you can find that some of these large N physics, even with system size like 12 or so, or 16, you can see some of this physics here. Okay. So you can again ask that what happens to this kind of effect of Goldstone modes in this calculation, and you can indeed very nicely see that this kind of crossover that I mentioned earlier. So if you look into this kind of C fermions, their Green's function has a crossover from 1 over square root of omega to square root of omega, and so basically just to summarize, I will not without going into the detail. So you can see that this Goldstone mode fluctuation in the original SOIK model actually only affect the C fermions, and it has a transition from at certain energy from the square root of omega to 1 over square root of omega, whereas the other fermion, this initially non-interacting fermion, they actually almost have no effect of these Goldstone modes, and they basically remain like the large N result. Okay, so there is no change. So this is this is just to say that indeed there is some change at finite N of this physics when you look into such small system, but even then this physics seems to corroborate with the large N and fluctuation around large N result even for such small systems. Okay. So now you can ask further that whether this kind of transition in the many body level spacing, whether you can look into more carefully, meaning indeed whether there is a exponentially small level spacing near the ground state for p less than 1, and whether this really happens. So this is the exact diagonalization result. So I am just plotting the spectrum near the ground state, let's say some 100, 200 levels for p less than 1, 0.33, and p greater than 1, p equal to 3. And you can just by eye you can see that this drastic change happening even in this, again, as this small system, this large change of level spacing that is happening. Okay, so you can also calculate thermal entropy, and it compares well, quite well with the large N results. So many of the large N results seems to work fine. However, if you really try to see whether this level spacing is exponentially small or polynomially small, it is hard with such small system size. In fact, what we find that if you try to, so if you plot the level spacing as a function of n with a exponential scaling or with a polynomial scaling, both of them work fine, which is not surprising because the system size is quite small, let's say up till 20, because this is low energy spectra, so one can easily do till 20. So it's hard to say whether there is really this kind of exponential scaling to polynomial scaling transition is happening or not. But what is true that certainly you can find there is a transition. So you can nicely, so with the polynomial scaling you can certainly find that this p, this polynomial power is very large in the SYK side, meaning the level spacings are really, levels are really dense, and then there is a transition where the level spacing is much larger. Okay, so and you can see that there is a transition at p equal to 1. Okay, so you can see indeed this kind of transition that is happening even in this kind of exact diagonalization. Okay, so now you can ask that, so all these are fine. So some of the physics near the ground state seem to be looking like finite temperature physics in standard model. So then what happens to entanglement entropy? Okay, so will the entanglement entropy will also correspond to this residual entropy? So what is the relation between the entanglement entropy of the ground state with the residual entropy? Because people initially thought that this residual entropy will also be equal to the entanglement entropy. Okay, so then you can sort of relate to this black hole having this Bekenstein-Hawking entropy, which has an interpretation in terms of entanglement. Okay, but it seems that that's not true. So that's what, let me discuss that. So to calculate the entanglement entropy, what you do here, you choose a set of sites. Of course, there is no locality in this model. Everything is connected to everything. Let's say you choose some 3 sites out of these. So you can choose these sites in different combination. You can take some psi fermions, some C fermions, whatever you want, and you have a subsystem of Na sites. Okay. And what you can do, you can calculate this entanglement entropy at certain energy. Now, if you have a conventional short range models, then if you have a thermal eigenstate, then you would expect that if you take the system, the whole system large enough, then this entanglement entropy should be similar to the thermal entropy at that energy, okay, that you can calculate from the temperature. Now, for the SYK model, you have to be a bit careful, because SYK model is a long range model, and this correspondence between the entanglement entropy and the thermal entropy actually doesn't work here, that you can show. So what happens, what you can show instead, that the entanglement entropy at certain energy will be equal to thermal entropy at certain other energy. Okay, so there is a mapping that you can do, but because of the fact that there is a boundary term which is long range, so you cannot really find out a subsystem A because the boundary term actually crucially affects the entanglement. Okay. And another thing is, you will always get a volume law entanglement because it is all to all, you can't get anything else. But what you can show by some arguments, as I said, that this entanglement entropy will be related to thermal entropy at certain energy, and you can put some bound on this entanglement entropy using some arguments. So first of all, the trivial result, so when you have this subsystem size versus the total system size going to 0, then you would expect that this to be log 2, the maximally entangled state. This is not surprising. So you will get log 2 into Na. However, if you go to a limit where this Na by n is finite, then you can show that this is there is some bound of entanglement entropy which is given by some formula with some energy appearing and the ground state energy appearing. So you can obtain this, but this is only a bound. This is not a rigorous calculation of entanglement entropy, but you can bound this entanglement entropy. Okay, so you can ask that what happens to entanglement entropy, whether it qualitatively changes from this non-Fermi liquid to Fermi liquid. And in fact, what you find that there is no real qualitative change. First of all, it is always volume law. There could not be any area law here. Then what else can really change? The original thermal entropy, of course, goes from extensive to non-extensive. So it goes from entropy density goes from finite to 0. But here nothing really can happen. So what you find if you calculate the entanglement entropy, then indeed when you go to a limit, so this is entanglement entropy as a function of the subsystem size with a total system size, let's say 12. So what you find that indeed at low values of Na by n there is this slope, and it is exactly given by log 2. Okay, so what you expect from this calculation, and when you go to the finite fraction of the subsystem, then you have some behavior, and you find that near the transition the entanglement entropy is the largest. Okay. So nothing much really happens in the entanglement entropy. So it has to be volume law. So then, so I think the conclusion that I will draw from this, that this transition that I mentioned, so which will be like a black hole transition, because you are, I mean, if you have some holographic description, it's really there is nothing much happening to the ground state across this transition. It is really the many body spectrum that is changing near the ground state. So it's not a transition in the ground state. No, because it's proportional to the number of sites in the subsystem. Okay. Yeah, I mean, so in this case it's hard to define because there is no dimension here. So generally you define the area law by L some lengths with L to the power d. But here, I mean, I mean, it has to be always proportional to the subsystem size. Nothing else can happen. Okay. Or constant, yeah, but yeah. No, I mean, it cannot be really constant, right? It has to be proportional to this thing. I don't think there is anything that can happen, anything else that can happen. Okay, so actually you can now reverse back this question. You can ask that can we actually calculate this entanglement entropy in the large n limit, okay? So actually we developed a method where you can, and we think that this method is kind of new. So it was developed by Arijit and me, and also independently by Rajdeep and Sharonno, I think, who is here. So we actually developed a method, and this is still very much work in progress, but using this method, so I will not be able to go into this method, but you can actually calculate entanglement entropy for interacting fermions, and we actually can calculate this entanglement, at least Renyi entropy for SOIK in the large n limit, okay. And what we find is, okay, I mean, maybe seems surprising, but not completely surprising. So let me just discuss this and stop. So what you find is, so if you look into the, we can calculate the second Renyi entropy and only numerically, and this result is for n tending to infinity. Okay, so we are calculating Renyi entropy for n tending to infinity limit. And what I am plotting here is the second Renyi entropy as a function of Na by n, where Na and n both are infinity. Okay, but Na by n is this fixed limit. So what you find is this surprising. So what we are trying to do, we are calculating this entanglement entropy at finite temperature and trying to take the t tending to 0 limit. Okay, that's how generally this kind of field theoretic method you calculate entanglement. Now what it turns out that if you look into this, so if you have such a plot, what you expect that at Na by n equal to 0 and Na by n equal to 1, the entanglement entropy should go to 0, okay, at ground state at t equal to 0. At any finite temperature, this value Na by n, where the subsystem is the whole system, is basically should be the entanglement entropy at a temperature T by 2, okay, because you are calculating Renyi entropy. You can argue that it will be thermal entropy at this point at T by 2. Now, because the SOIK model has this residual entropy, what you find, so this from this calculation, that this entire Renyi entropy also approaches this residual entropy at this value. In fact, if you try to extrapolate this Renyi entropy at this point, where you know it should be the thermal entropy at a temperature T by 2, what you find that this Renyi entropy actually approaches a value which is equal to the ground state residual thermal entropy of the SOIK model. So in other words, if you try to do a large n calculation, you can never recover the quantum entanglement of the ground state. Okay, so this limit again, just like you cannot recover the exact ground state entropy, which is actually 0 in the SOIK model, you cannot recover the quantum entanglement of the ground state. Okay, so this is so this is the result of large N. So you can ask whether this is an artifact of the calculation. It is not. So we have done the same calculation for Fermi liquid, and in fact you can show if you have a Fermi liquid, then in fact as you take the temperature lower and lower, this value, which should become 0, actually approaches quite close to 0. We have not gone to enough low temperature, but we can go. I mean, this is a work in progress. So basically, just to summarize the SOIK model, so this is where I will stop. So SOIK model in some sense is kind of weird. So what I tried to discuss is that so the model that I discussed has a kind of an unusual transition where you have a phase where near the ground state you sort of mimic the high energy physics of many conventional model, and as a result there is a thermalizations and this kind of effects, maximal chaos, etc. And then you can actually tune this transition, non-trivial transition, and go to some kind of other chaotic fixed point where you have a Fermi liquid which has 0 residual entropy, just like you expect in the standard model. And so what I am not going to discuss is the quantum quench. So you can actually do a quench of this model, both in exact diagonalization and using some Keldysh field theory exactly. And you can actually show that this non-Fermi liquid and Fermi liquid indeed have a very different thermalization behavior, even far from equilibrium. Okay, so I will not discuss that. So with that I will stop, and thank you for your attention.
Thank you. Yes. Is it meaningful to ask about level statistics across this transition, or not really? Because on the right, my understanding is that you don't kind of have
That's right.
enough density of states.
Yeah, so we have actually looked into the level statistics here in the non-Fermi liquid side. So this you can, because you have so many levels, you are right. So you can actually depend. So SOIK model, depending on what is the system size, you can actually it can have GOE or GUE, and those things you can actually check here. And people have done earlier also. I mean, yeah, it's right. It's hard to. You have to really go to somewhat higher energy to do any statistics. So at very low energies, this statistics probably not very meaningful.
If you plot this lambda over t across the transition, so it decreases and then becomes flat. So do you see?
Yeah, so lambda over t, if you take t tending to 0, is just constant and then is jump.
I'm saying as a function of p.
As a function of p, but if you're calling lambda L by t, right, temperature. Yeah, so lambda L by t, so in the Fermi liquid it's t square. So but so yeah, so lambda L by t tending to 0 is like constant and then 0 at t tending to 0, because in the Fermi liquid it's t square, so t square over t will give you t. When you try to take t tending to 0 limit, then
in the non-Fermi liquid, it's only at low temperatures that it's t.
That's right. Higher temperature, there are some other. So we have calculated all those earlier. Yeah, all the full temperature dependence is known. I mean, at least numerically.
So, thank you very much.